A lot of electricians who came up doing residential work hit a wall when they first deal with three-phase. The terminology sounds more complicated than it is. Once you understand what's actually happening, it makes complete sense. Let me walk you through it. Hey, welcome to Hardwired Trades. Today's topic is three-phase power, what it is, why it exists, and how it actually works in the field. This is aimed at guys who understand single-phase systems and want to get comfortable with three-phase. We're keeping it practical. No theory for theory's sake. Single-phase versus three-phase, the core difference. Most homes in the US run on single-phase power. You've got two hot legs, each 120 volts to neutral, giving you 240 volts between the hots. Simple. Three-phase power adds a third hot leg. Instead of two phases carrying the current, you have three, and they're timed 120 degrees apart from each other on the sine wave. Why does that matter? Because when one phase is at its peak, the others are at different points in their cycle. The load is always distributed. The power delivery is smoother. You get more power capacity from a given wire size. That's the practical advantage of three-phase. More power, more efficiently delivered. A three-phase system can deliver more power than a single-phase system of the same amperage because the current is always flowing on at least one phase. There's no zero crossing point where all three phases are simultaneously at zero. The power delivery is continuous and balanced. Think of it this way. Single phase is like paddling a canoe with one oar. You're paddling on one side, then the other, back and forth. Three-phase is like a boat with three paddlers who are always offset from each other. There's always someone delivering power stroke, and the boat moves smoothly and continuously. Where you find three-phase. Three-phase is everywhere in commercial and industrial work. You will almost never see it in a standard residential home. Where you will see it. Commercial buildings with large HVAC systems. Industrial facilities with heavy motors, pumps, compressors, machine tools, data centers, hospitals, manufacturing plants, large electrical panels in multi-tenant commercial buildings. If you're doing commercial or industrial electrical, you need to understand three-phase. If you're staying residential your whole career, you'll rarely encounter it. But if you want to move into commercial or industrial, and if you want to go after higher-paying work, understanding three-phase is a prerequisite. The two types, Y and delta. Here's where people sometimes get confused. There are two common configurations of three-phase power. Y, also written as Y, and delta. YY configuration has a neutral wire in addition to the three hot legs. Each phase is 20 volts to neutral. Phase to phase between any two hots is 208 volts. This is what you typically see in commercial service. 120 to 208 volts, three-phase, four-wire, great for powering both single-phase loads like lighting and outlets and three-phase equipment. Think of Y as being like a star. The neutral is at the center. The three phases extend outward. Each phase is the same voltage to neutral, 120 volts. But between any two phases, you measure 208 volts because you're measuring across two legs that are 120 degrees apart. Delta configuration. No neutral wire. Just three hot legs, common in older industrial settings and some specialty applications. Phase-to-phase voltage is typically 240 volts or 480 volts, used heavily for driving motors. There's also a high-leg delta or wild leg configuration that has a neutral but one leg. The B phase is around 208 volts to neutral instead of 120 volts. That's the wild leg, and you need to know not to put 120 volts loads on it. Older industrial panels with this setup will have the B phase marked in orange. Voltages you'll encounter. Most common three-phase service configurations. 120-208Y, commercial standard, 120 volts to neutral, 208 volts between phases. 277, 480Y, used for larger commercial and industrial, 277 volts to neutral, 480 volts between phases. This is where your big lighting ballasts and large motors run. 240-volt delta, older industrial motors. 480-volt delta, heavy industrial motors. On a 277 480-volt system, the 277-volt is used for fluorescent and LED lighting ballasts. That's why commercial lighting runs at 277 volts in most office buildings and warehouses. The 480-volt is for motors, large HVAC equipment, and major mechanical loads. Knowing this helps you understand the equipment specifications when you're reading commercial drawings. Three-phase motors. Why three-phase is built for them. Motors love three-phase power. The reason is rotation. A three-phase motor uses the three staggered phases to create a rotating magnetic field. This is what spins the motor. It's more efficient than single-phase, produces smoother torque, and the motors are simpler and more reliable. If you're doing any industrial work, you'll be wiring three-phase motors constantly. The wiring is straightforward once you understand the configuration. 3 hots in, motor spins. One practical thing to know, three-phase motors can run backwards if any 2 phases are swapped. Always check rotation direction before putting a motor into service. On pumps and fans, running backwards even briefly can cause damage. On some centrifugal pumps, running backwards can destroy the impeller within seconds. Swap any 2 leads to reverse rotation, that's all it takes. Calculating power on a three-phase system. On a single-phase system, power in watts is volts-amps. On a three-phase system, you add the square root of 3, which is approximately 1.732, to account for the three-phase factor. P equals Vxi x 1.732. So a 480-volt three-phase motor drawing 10 amps is running at 480 by 10 1.732 was approximately 8,314 watts, or about 8.3 kilowatts. This formula comes up when you're doing load calculations on three-phase panels. Know it. You'll also use it when you're sizing wire for three-phase motors. Knowing the actual wattage and current lets you verify the nameplate data and select the right wire gauge. Reading a three-phase panel. A three-phase panel has 3 bus bars, A, B, C phases, instead of 2. Breakers snap onto 1, 2, or 3 phases. Single-pole breaker, 1 phase, used for 120 volts or 277 volt circuits. 2-pole breaker, 2 phases, 208 volts or 240 volts. 3-pole breaker, all 3 phases, for 3-phase equipment. When you're balancing loads in a 3-phase panel, the goal is to distribute the load as evenly as possible across all 3 phases. An unbalanced panel, where one phase carries significantly more load than the others, causes neutral current, increases losses, and can cause overheating. Check the load balance as part of your panel work. A clamp meter on each phase at the panel will show you the imbalance. Good panel work means balanced phases. 3-phase isn't scary once you break it down. It's just more capacity, more efficiently delivered. If you're moving into commercial or industrial work, this is fundamental knowledge. Subscribe to Hardwired Trades for more content like this, and drop a comment if there's a specific 3-phase topic you want me to go deeper on. Practical troubleshooting on 3-phase systems. When you're troubleshooting a 3-phase problem, the first thing you check is whether all 3 phases are present and roughly equal. Grab your multimeter and check phase-to-phase voltages. A to B, B to C, A to C. On a 208 volt system, they should each read approximately 208 volts. On a 480 volt system, approximately 480 volts. If one reading is significantly off, say you get 208 volts, and 0 volts, you've lost a phase. That's a utility issue or a problem with your service entrance. Also check phase to neutral on a Y system. All 3 should read approximately 120 on a 120 208 volt system, or 277 volts on a 277 480 volt system. A voltage significantly lower than expected on one phase with others normal often indicates a high resistance C connection somewhere in that phase. Phase-to-phase imbalance greater than 2 to 3% is worth investigating. Even small imbalances cause motors to run hotter and less efficiently, and significant imbalance can cause motor failure over time. VFDs and 3-phase variable frequency drives, VFDs, are increasingly common in commercial and industrial applications. They're used to control the speed of 3-phase motors by varying the frequency of the power supplied to them. What electricians need to know about VFDs? They have specific wiring requirements, and they're sensitive to certain installation issues. Input side requires proper protection, fusing or circuit breaker per manufacturer. Output side goes directly to the motor. No switches, contactors, or capacitors between the VFD output and the motor. VFDs are also sensitive to ground faults and can cause nuisance tripping of standard GFCIs. Don't put them on GFCI-protected circuits without consulting the manufacturer. VFDs are becoming more common in HVAC systems, pump applications, and conveyor systems. Understanding them is becoming increasingly important for any electrician doing commercial work.